We need that in the microphone.
Okay. Homework due Monday, 5 p.m. So we're beginning our discussion on iterative methods, and let's just review a few points. So here we have iterative methods. And the basic idea, as I've said before, is that we want to solve AX equals B. And then we break this up into MX equals NX plus B. Or it may actually have been changed by the time we've transformed it in this fashion. That's not necessarily important. And that's X equals M inverse NX equals plus M inverse B. And this matrix, M inverse N, I identify as a matrix B, and if all the eigenvalues of B are less than 1, that ensures convergence. Now, so that's the general theorem, and well, you can state a lot of other theorems that are very useful too. But in this class, what we want to study is not only the different ways we can split a matrix, but how useful they are in different circumstances. So let me just give you a variety of matrices. For instance, A, okay, it can be symmetric and positive definite. And this is the case that's most well understood. Symmetric, positive definite matrices, we know very well how to solve such systems of equations. And then A can be diagonally dominant. So that's another important class of matrices. Let's see. Of course, you can A equals A transpose indefinite. For instance, you could have an A that looks like, what should I call it? C, B, B transpose 0. And such matrices occur very often. This is a very indefinite matrix, but it's structured indefinite. We know exactly if C tends to be positive definite. So this comes up in lots of different applications. And it's really an important class of matrices. Okay. Well, the most general matrices, of course, is A is not equal to A transpose. That is just a non-symmetric matrices. But even there can be specialized cases. And I'll just mention two of those. And there are special methods. One would be that X transpose AX is positive. So this is called a positive real matrix. So the matrix is not symmetric, but if you look at this quadratic form for any X, it's positive definite. And there are lots of examples where this comes about. Much of my motivation is in cases where you're solving partial differential equations. But this real positive is an important category. Then there's also A equals, let's say, C plus ID, where C is symmetric and D is symmetric. So both matrices are symmetric. That doesn't make this matrix Hermitian. Hermitian matrix is different. So the real part is symmetric, and the imaginary part is symmetric. And this comes up in applications again connected with PDEs. So there's there are methods for each one of these categories, and there's a general method. We'll talk about that too for general non-symmetric matrices. So as I said, what we consider is writing down a matrix in some form. And last time I looked at this, xk plus 1 equals I minus alpha A xk plus alpha B. So you see I've modified B in some fashion. At any rate, this is called the Richardson first order method. And you can see immediately, by the way, in implementing this, it has nice parallel implementations. And then we were concerned with the choice of alpha. That's an important thing. So let me just write that down again. Suppose A has eigenvalues, mu1, mu greater than, we're going to assume it's positive definite, mu2 dot 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 down to mu n, and they're all positive. And B of alpha, which is equal to I minus alpha A, I call those eigenvalues lambda I, and it's just equal to 1 minus alpha mu I. Okay. So, after all, you multiply a matrix by a scalar, multiplies the eigenvalues by the scalar, you have a multiple of the identity, and that just shifts the eigenvalues by 1. Now, let's look at the graph of this. That's what I did the other day. And this is the alpha axis. And the question is how to choose alpha. For one thing, we'll notice that alpha better be positive. That is, here would be, let's take lambda 1. So lambda 1, all the eigenvalues will start out as at 1, okay, and then and then they're linear. This goes down like this, and I should draw this a little further. This is linear. So this is 1 here, and let's make this equal to minus 1 over here. Okay, I'm sorry, my graphic arts department doesn't always work so well. And this quantity here, this is 1 over mu 1, right? When alpha equals 1 over mu 1, you get a 0 for this first eigenvalue, and then you keep on getting all these other eigenvalues. Okay, so this, let's say, could be associated with mu n. So this would be 1 over mu n, and eventually it becomes minus 1. And as I showed the other day, the best choice is when lambda 1 or minus lambda 1 is equal to lambda n. In other words, let me go. Let's see if I can. Medium. Oh. Well, trying to. Oh, here we go. That's the point. That's the pen settings. What is this guy over here? Well, here's this curve or straight line, and here's this straight line. Now, one thing you can see is that this method is going to converge, will converge for any alpha, now, or alpha has to be positive. So you can see, as long as alpha is positive, there may be convergence. But where does divergence occur? It occurs at this point over here. See, remember, this curve here, or straight line connected with mu sub n, is the largest eigenvalue in magnitude now, and this straight line here is the smallest eigenvalue. So when these two lines, that's what defines our optimal alpha, when they're equal in magnitude, something like that. And then as soon as alpha reaches this value over here, oh, I said over here, I was wrong. As soon as alpha reaches over here, then you'll notice all eigenvalues will start being, no, it's over here. No, I better get my story right. As soon as alpha reaches over here, then you know that you're in trouble. So let's see. This says that when alpha, I better get this, is, less than or equal to 2 over mu sub n. That's this value over here. As soon as we get to that value, then it will diverge, because all the eigenvalues will be greater than -1. So this spells out the convergence of the method. Okay. So that's the interval of convergence. And the optimal alpha, I didn't say it this time so much, is lambda 1 plus lambda n. So you need to know something about this extreme value. Okay. Now, what is the value of lambda n when you use that extreme value? That would tell us the best rate of convergence. So what we have to do is look at lambda 1, I'll call this value alpha hat, is equal to, okay, and then we would have from our analysis that this is equal to, let's see, it would be, lambda, no, yes, it's connected with lambda 1 or lambda n. Lambda n is 1 minus 2 over lambda 1 plus, this should be mu 1 plus mu n, okay, and this should be equal to mu 1 plus mu n minus 2 over mu 1 plus mu n, and that's it. That minus 2 is screwing me up. Oh, 2 times mu 1. Right? This is alpha, this portion here, and then this is mu 1 over mu 1 plus mu n. Mu 1. So times mu 1, and this is just equal to mu n minus mu 1, okay, divided by mu 1 plus mu n, okay, and this is equal to, now let me normalize this, 1 minus mu 1 over mu n over 1 plus mu n, plus, or it's mu 1 over mu n plus 1. Okay. So this is this is lambda n, and if we take minus lambda n, that's really what we need to know. Then we can rewrite this as kappa, the condition number minus 1 over kappa plus 1. Okay. So the rate of convergence is heavily dependent upon kappa. So kappa is the condition number of A. So you can see if you have a very large condition number, this will be very close to 1, and you'll have very slow convergence. So even if you have the best choice of parameters and know them exactly, you don't get very good convergence here. What sometimes one does is replace AX equals B by D inverse y equals dB. Okay, so D is a diagonal matrix, D diagonal. And we replace A by DAD, and the question is, can we choose a D so the condition number of DAD is less than or equal to the condition number of A? And the answer is yes, and I'll say something about that a little later. So you still don't get terrific results, but you can get really an improvement very often by rescaling the problem. Okay, so this is the Richardson method is a classical method. It depends upon a knowledge of the largest and smallest eigenvalue or some bounds. Getting a bound on the largest eigenvalue isn't so difficult, but a bound on the smallest eigenvalue, that turns out to be difficult at many times. Okay, now I'm going to just switch over to another kind of decomposition, and let me just explain the problem. There's what's called the Helmholtz equation, and sometimes you have an equation of the form minus the Laplacian of u plus sigma xy times u equals f. And the domain, and then we have u equals g on the boundary. Now, the domain is going to be rectangular. And we're going to talk about finite differences. So this is a classical problem. You have Poisson's equation plus sigma xy. We'll assume sigma xy is positive or greater than or equal to 0. And so we have almost a nice problem to solve, except for the sigma. And the question is how to derive an iteration scheme. So here's one idea. We write minus delta uk plus 1. Here I write in the continuous form, or the discrete form, it's all the same, plus sigma xy uk equals f. So I guess at u0, and then, of course, this goes on to the right-hand side, and then I solve Poisson's equation on this rectangular domain. That gives me u1. I put u1, stick it in here, and put it on the right-hand side, and then solve for u2, and so forth. So we solve a sequence of problems. It's, again, a splitting. You can see it's equivalent to splitting of the operator into an m. This would correspond to m. And n corresponds to this diagonal matrix. Okay. So remember, A would look something like this, just to recall some of the previous things. T on the diagonal and minus I above and below. Okay. Okay, so now let's see how we can solve this system. And sigma, let me write it this way. It's just a diagonal matrix, sigma 1, 1, sigma 1, 2, dot, 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 sigma n, n. I'll just assume it's a square domain, where sigma ij is sigma evaluated at xi and yj. And as I said, it's a positive quantity. Okay, so what does our scheme look like? And what we really have is this matrix A divided by h squared. So h squared is the mesh size. Okay, so the A I wrote down didn't reflect the mesh size, but you multiply it by 1 over h squared times uk plus 1 equals sigma uk plus b. All right, and that says, of course, uk plus 1 equals h squared times A inverse sigma uk plus A inverse times b. So if we use our usual manipulations, the error, ek plus 1, the 2 norm we'll take, is bounded above by the norm of h squared A inverse sigma times ek, the norm of ek. Okay. And this is less than or equal to h squared times the 2 norm of A inverse times the 2 norm of sigma, just using our norm inequalities, times the 2 norm of ek. Now sigma is a diagonal matrix, and if you want to look at the 2 norm, you just have to look at the maximum element in it. So this would be less than or equal to h squared times the norm of A inverse times the max of all the sigmas times ek. Okay. Now, if you look at what we've done previously, it turns out, you see what you need, what's the 2 norm of A inverse? It's 1 over the smallest eigenvalue of A. So to get the 2 norm, this is equal to h squared times the smallest eigenvalue of A inverse, which is, if you look in the previous discussion about fast Poisson solvers, 4 minus 4 cosine pi h, okay, times, again, this maximum sigma ij times the norm of ek. Okay. Now, if you do a little, you can rewrite this quantity here as h squared, and then if you start playing around with this, you discover this is 8 sine squared pi h over 2 times, again, the max sigma ij ek. Okay, so finally, let's do it this way. Finally, this is equal to 1 over 8 times, and then we would have 1 sine pi h over 2 over h squared times the max sigma ij times the norm of ek. Okay. And it doesn't take long to figure out. This has you have to throw in the 8. So let's see. If I made this h over 2 and I made this into a 2 over here, I guess that would be the same thing. Okay, so now if you take the limit as h goes to 0, this turns to be equal to what? More or less the max sigma ij, and then this ratio here turns out to be 2 times, and you know, if you take sine constant h over h and take the limit, this turns out to be just pi squared. Okay, times ek 2. And that's actually even a bound. This converges very quickly. Okay. So what does this show? So this says if the max sigma ij over 2 pi squared is less than 1, method will converge. So the iteration consists of solving Poisson's equation repeatedly on a rectangular mesh, and just solving it very straightforwardly. You can see if sigma ij, the max, is small, and this number here is about 20. So any number less than 20, it's going to converge, and it might converge very fast. And an important thing is that that method is essentially independent of H. Right? So the rate of convergence, if you choose H equal a 20th or H equals 100th, the rate of convergence will be more or less the same. This isn't quite exact, but it's more or less the same. But the amount of work differs, right? Because each one of these calculations requires the solution of a Poisson equation. So the Poisson equation solvers really depend upon H. So the number of, so this is sometimes people get confused about this. Just by showing that the rate of convergence is essentially independent of H, that doesn't mean that it's necessarily going to be converge quickly, because you may have to do a lot of computation to get that sort of rate of convergence. So ultimately, we're always looking for methods that not only converge fast, but with as little work as possible. So that's really the best way we can go. Okay, so this is another kind of iteration, but now I'm going to return to ideas about choosing a variable alpha k. So in our earlier discussion, we had xk plus 1 equals xk plus and now I'm going to put alpha k rk. So I'm going to choose a sequence of parameters rather than one parameter. And now let's see. And rk is equal to b minus axk. So let's substitute into here. So let's see. What do I? We would have rk plus 1 equals b minus axk plus 1, okay, equals xk what did I do here? Okay, it's equal to b minus a times xk plus 1, so that's equal to xk, okay, plus alpha k rk, just substituting in this expression into here. So this is equal to rk minus alpha k ark. So this is a recurrence relationship for the residual, more or less just the same as we had for the error equation. Okay, and now here's the thing. What we would like to do is look at rk plus 1, A inverse rk plus 1. So we stick in an A inverse here. That's our sort of our weighted norm. Its advantage is that it's very convenient, especially, although it's not really necessary. You can do the same equations without this. Okay, so this would be equal to, and then I just take this expression that I had earlier. This should have been RK, shouldn't it? It should be RK transpose I minus alpha A transpose A K, A inverse, times I minus alpha K A. Yeah. And I'll multiply this all out together. And here's what I get. This is equal to, now let me get this straight, RK transpose A inverse RK, that's just the first term out of all this, minus 2 alpha K RK transpose RK, okay, plus alpha K squared RK, and then A RK. Okay, just multiplying this whole expression out. And now the idea is to look at the gradient. So this is some functional. We know what RK is. In theory, you know what A inverse is. How do we choose alpha K to make this expression as small as possible? This is what's called the method of steepest descent. So what we want to do is take the derivative of this expression, let me call it star, with respect to alpha K. And so that's going to be equal to minus 2 RK transpose RK plus 2 alpha K RK transpose A RK. Okay. So the optimal choice, alpha K hat, is equal to RK transpose RK. Okay, so Rayleigh, it's going to, well, the inverse of a Rayleigh quotient, RK transpose A RK. So it's a very simple calculation, and you notice in our previous discussion of the Richardson method, first order method, you just chose an alpha once and for all, and that was good enough. But now we're going to choose a different, and that means more calculation, right? You have to compute this inner product and this inner product. and you can see even how large this will be. You know, it's often very useful to have these kinds of bounds because it tells you information. That is, if you have a matrix A and look at any quadratic form like this has to be between the largest eigenvalue of A and the smallest eigenvalue of A. And therefore, this quantity, alpha K hat, has to be less than or equal to 1 over the smallest eigenvalue of A and greater than or equal to 1 over the largest eigenvalue of A. This is just an interesting inequality, and it just tells you something about the alphas. We'll get more information about the alphas as we go along. Okay. Now, let's see, what we're going to try to study the rate of convergence. And if I look at RK plus 1 transpose A RK plus 1 over RK plus 1, if I look at this quantity, which I want this quantity. Remember, we're trying to minimize this expression. And then I take the optimal value of alpha K, and when I do so, I get that this is equal to RK transpose A inverse RK, okay, minus RK transpose RK, and this whole thing squared over RK transpose ARK. Okay? So we finally get something of the following sort, that the norm of RK plus 1 in the A inverse norm, okay, and I have a square on here, divided by the norm of RK in the A inverse norm is bounded by 1 minus RK transpose RK squared over RK transpose ARK times RK transpose A inverse RK. So we would like to be able to say something about this quantity. It's 1 minus some positive quantity, and if we know all these guys, if we have these ratios, then, and we can bound this by something or other, then we'll be able to bound the error after k iterations. And what we're going to show in just a moment is the use of a very important inequality. So let me just mention that, and I won't prove it or anything. So this method of steepest descent was first discussed at length by a Russian mathematician called Kantorovich. And what he did, he proved that if you take this product as you see, you have something like this already. This is less than or equal to kappa minus 1 over kappa plus 1 squared. Okay? So this is the famous Kantorovich inequality. So Kantorovich was a Russian mathematician, and he wrote this monograph on the use of functional analysis in applied mathematics. And this monograph was translated in English, and the person who served as the editor for that was George Forsythe. Forsythe was the founder of our computer science department. And there's a little footnote there, and Kantorovich made some sort of claim, and Forsythe said, I don't really understand I don't think he's right about this. I don't think he really, that it had been shown elsewhere. And so then immediately a lot of mathematicians jumped into the game, and they start proving things. And there were maybe 10, 20 papers immediately proving the Kantorovich inequality, showing how it's a consequence of some other inequality, and just giving some very interesting results. And it stimulated a whole activity. I don't know, just to tell you, mathematicians they like to jump on the bandwagon. They see some problem, and maybe Mr. X solves that problem, but then another person wants to solve it a little more generally or a little differently, and they solve the problem too. So once you highlight a problem in mathematics, and unless it's an impossible problem, then a lot of people want to solve the same problem. So Kantorovich, he wrote this inequality, and Forsythe, by making that note, encouraged a lot of people to work on it. So many papers appeared. Now the interesting thing is, the results, this little result that I have here, they're rather important. They turn up in lots of different places in optimization theory and statistics and so forth. Finally, a friend of mine, he had a student who wrote her thesis on this inequality and its use in statistics, and there were like 120 references. And this friend of mine, who was a bibliophile, he traced it back to some guy, a German guy who was living in Argentina and had done the work in the 1920s. but alas, before my friend could actually get down to Argentina, the man who originated it died. So it's known as the Kantorovich inequality, and it's a very useful inequality. What it does then, if we have this inequality here, it proves the following. Well, that the norm of ARK plus 1 in the A inverse norm over RK, the norm of RK, well, I'll put a square on both of these, and the A inverse norm is bounded by kappa minus 1 over kappa plus 1 squared. And if you use this result repeatedly, what you find is the norm of RK over R0, this is all in the A inverse norm, is bounded by kappa minus 1 over kappa plus 1 raised to the kth power. So you can see this is more or less the same result as the Richardson method, where you selected the parameter in advance. So the steepest descent and the first order Richardson asymptotically have essentially the same rate of convergence. But in the Richardson method, you have to know the parameter ahead of time, whereas the Kantorovich method, or the steepest descent, you dynamically compute the coefficients. Now, so you get the same rate of convergence, but the price you pay is that you have to do a lot more calculation. You have to calculate these alpha k's as you go along, and that really increases the amount of computation. So rates of convergence are important, but asymptotically, what you really want to study is the amount of work required for different algorithms. Here it's essentially twice as much work to do this calculation as it would be just to do the straight Richardson method. Okay, well, we'll go to another generalization that'll take up. So a lot of the stuff, which is interesting, and we don't stress this so much anymore, is dependent upon approximation theory. And approximation theory and linear algebra often go hand in hand. And many of these problems connected with iterative methods are really problems when you ultimately come down to the details, turn out to be problems in approximation theory. So good. So let's break for 5 and get on. Okay. So,
are you here next week?
Yeah, till Wednesday.
You're here till Monday and Wednesday?
Yeah, lecture on Wednesday.
So no, what about Monday?
I'll be here.
Monday,
yeah.
But not next Friday?
No. And there's a week off. And then the week after that is Thanksgiving week. Yeah. So I'm going to Zurich, and I'm giving talks and getting an honorary degree and all sorts of things.
I haven't seen Michael Saunders yet, but is he pretty thrilled about it?
Oh yeah, did I tell you that?
You mentioned that.
Oh, he like everybody, he realizes other people had to do a bit of work, but it was for him it's such a pleasure to help him out, so he's very happy. So
yeah, we tried to find the announcement on the. Has it been announced yet?
No, but I want to put out an announcement in the digest. Do you read the digest at all?
Not yet. No.
Do you get it?
Digest? I haven't subscribed.
Oh, it's easy enough to do. Yeah. At any rate, I'll send a notice to everybody. as soon as I formulate it properly.
Uh-huh.
But no, it's he's one of the world's nicest people, and it's such a nice thing. Yeah. So I was miserable yesterday, and I was in I went to see the doctor, and the first thing he said, well, we'll do some tests and just try to figure out what's wrong. And then he called me. philosophy, I'm trying to emphasize, that there are all kinds of different ideas that float around, and sometimes these ideas are useful when they're invented, then they fall by the wayside, and then at some future date they come back again because they have certain properties that are very useful. So far we've talked about the Richardson method, steepest descent, and now we'll talk about even another extension of these ideas. Now, the method so far we talked about had one parameter, and then we computed a parameter, and we showed how to choose an optimal parameter. And then we had the idea, well, okay, maybe we should dynamically choose the parameters, and we know how to do that now. But here's another possibility, that somehow we have a sequence of parameters. So xk plus 1 equals I minus alpha k a xk plus alpha kb. And again, these alpha k's, we're going to try to determine them a priori, or we'll investigate how to choose them possibly beforehand. So if we look at this equation, and we look at the error equation, x minus xk plus 1, then very quickly you see that this term drops out. That's I minus alpha ka times x minus xk. Because this term is, we can easily show that this term is not of interest in studying the error equation. So this is the error equation. ek plus 1 is equal to I minus alpha ka times ek. So this is a matrix difference equation. We've seen this quite often now. You can see E1 would be equal to I minus alpha 0 of A times E1, E0, excuse me. And then E2 is I minus alpha 1A times E1, and so forth. So, oops, wrong direction. If we continued this, we would get the following, that just by recurring on the equation, that Ek is equal to I minus alpha k minus 1a times I minus alpha k minus 2a I minus alpha 0a times E0. In other words, Ek is some polynomial of degree k in the matrix A times E0. So we've already shown how to choose the optimal polynomial in some sense when k equals 1. And the question is, what other possibilities are there? Can we figure out a better way? And we're going to see again some use of approximation theory that I mentioned to you already. So let me just recall a couple things for you. And again, I sometimes emphasize bad methods as well as good methods because they're insightful, or they may be insightful. So let's assume this matrix A has n distinct eigenvalues, as we have in the past. So they're distinct. I should write inequalities. So these are the n distinct eigenvalues. And now there's a theorem called the Cayley-Hamilton theorem. And it says every matrix satisfies its own characteristic equation. So in other words, if you have psi of lambda equals the product of lambda minus lambda I equals 1 to n, equals 0. So this is the characteristic polynomial. And by Cayley theorem, okay, so we know every matrix has a characteristic polynomial because we've assumed these eigenvalues are distinct. It makes it slightly simpler. And the Cayley-Hamilton theorem says psi of A is equal to the product A minus lambda I, and that's equal to 0. So we could have something like this is equal to, let's say, the product of 1 over lambda I A minus I. And I guess I've pulled out a lambda I to the nth power. That doesn't really make any difference. Or just the product of the lambda i's. That's still equal to 0. So if we knew the eigenvalues of the matrix, you can see that we could easily establish a method for computing. I could rewrite this. Let me do it this way. We could rewrite this psi of A. I'll call it psi tilde. It doesn't matter. It's just a renormalization. Equals pi of I minus 1 over mu I times A, and that's equal to 0. So, what does this say? It says the following: if you know all the eigenvalues of A, which I called mu I, then alpha I equals 1 over mu I I minus mu I. I guess is alpha I minus 1. In other words, if you knew the eigenvalues, you know you can actually create a polynomial whose roots are just what you want, and the nth degree polynomial will be equal to 0. And this method is no good, NG. So this really, again, distinguishes between mathematics and numerical computing. Even though, you know, mathematically something is equivalent and you could solve a problem in such and such a way, it's a terrible way to go, and it doesn't really solve the problem. So it's you have to avoid this kind of method. If you had a very large matrix and you knew all the eigenvalues, it's not so likely you would, then this tells you how to get the solution, and it would not be a very good approach to the problem. But we still can think about this business of a polynomial. That is, here we had EK equals a polynomial in the matrix A times E0. Okay. And then this says that the norm of EK, the 2 norm, over E0 is bounded by the 2 norm of PK of A. Okay. And this matrix, PK of A, of course, is symmetric, has a complete set of eigenvalues and eigenvectors. Here we go. So in reality, if we have a diagonal matrix, so for instance, suppose that A equals Q mu Q transpose, the 2 norm of PK of A is equal to what? The 2 norm of PK at mu 1 PK up to mu n. Okay. So, here's the idea. We're not going to try to minimize in the entire interval, but we'll just say, we'll fix k, and we'll say the following. We would like to minimize the maximum value of pk of lambda, of mu I. Okay. That's our aim. Minimize, so we look at the max for all mu, and we want to minimize this with the side condition that pk of 0 equals 1. You can see that has to be satisfied by our. Okay. So amongst all polynomials, so if you're given n eigenvalues, you would like amongst all eigenvalues, all polynomials, the polynomial whose maximum is a minimum. Okay. And that problem has long been solved, and they're called Chebyshev polynomials. Chebyshev. Okay. And they're given in this way. I call, let Ck be equal to cos k cos inverse cos, that's inverse x for x less than or equal to 1 in magnitude, and it's equal to cos k cos inverse of x when x is greater than 1. Okay? So, all right. And for instance, the classical recurrence relationship for Chebyshev polynomials or for trigonometric functions like this, C0 is equal to 1, C1 of x equals x, C2 of x is equal to 2x squared minus 1. I have to normalize these in order to get the true Chebyshev polynomials. So these are trigonometric polynomials. And, if you write down, if you recall, see, everything goes back to things that you maybe knew in high school. Cosine k plus 1 theta is equal to cosine k theta cosine theta minus sine k theta sine theta, and cos k minus 1 theta equals cos k theta cos theta plus sine k theta sine theta. So if you add these two together, you get a recurrence relationship. You get cos k plus 1 theta is equal to cos k theta cos theta minus cos k minus 1 theta. Okay? In other words, if you look at this, ck plus 1 of x equals x times, there should be a 2 here, by the way, 2 ck of x minus ck minus 1 of x. So this is the recurrence relationship that you use for Chebyshev polynomials. You don't need to compute these trigonometric functions. if you want to compute the Chebyshev polynomial, you use this recurrence relationship. And if you have a particular xi you want to evaluate it, the Chebyshev polynomial, you just use these recurrence relationships. Now, actually, the Chebyshev polynomial has to be normalized. And the real Chebyshev polynomial is Tk of x is equal to Ck of x over 2 to the k minus 1 for k greater than or equal to 1. So this is really the Chebyshev polynomial. It's the normalized polynomial, and it's a very good approximation to 0. Okay, we have the Chebyshev polynomials. I won't bother to prove things immediately here, but they really are very useful in many different applications of numerical computing and in other areas too. So you have this 3-term recurrence relationship. Now, what do you need to know? If you're going to get the Chebyshev method to work, you need the zeros of this polynomial, and because they're trigonometric, you can write it all down. And I'll just write it down in this fashion here, that so it says AJK, or what I call them alpha JK, I'm sorry, alpha JK, is equal to, okay, B plus A over 2 minus B minus A over 2 cos 2J plus 1 pi over 2K. And it's this inverse. Okay. So these are these parameters. It's fixed for a given k. So if you choose k equals 3, that means you have to go through 3 iterations with Chebyshev polynomial. So you cannot terminate your algorithm before you do 3 iterations. You have to go through k iterations before you do a calculation. And so it's really required that you specify in advance how many iterations you're going to do. And if you want to go through another 7 iterations, then you would, if you wanted a 7th degree polynomial, you would just figure out these coefficients and go through 7 iterations. Well, the mathematical theory says if you do this, the error, EK over E0, in the 2 norms now, is bounded by twice, okay, square root of kappa plus 1, minus 1 over square root of kappa plus 1 raised to the kth power plus the square root of kappa minus 1 over the square root of kappa plus 1 raised to the kth power. And this looks like the square root of kappa minus 1 over the square root of kappa plus 1 raised to the kth power. So the Chebyshev method, what happens? What's the effect of the Chebyshev method? The rate of convergence no longer depends upon kappa, but now on the square root of kappa. That's a considerable increase. So that means if you use just steepest descent, and let's say kappa is 1,000, but if you use this with a knowledge of A and B and with several parameters, when this inequality really comes into play is a question in its own right. Then you can see things depend on the square root of kappa. Well, the square root of 1,000 is like 35, so it really makes a significant difference. So the Chebyshev method is really a powerful method. The only trouble is it doesn't work as prescribed. And why doesn't it work? and this is again the difference between mathematics and computation. In the mathematics, the ordering of these alphas doesn't make any difference. And if you can choose any set of the alphas in any way you want to. So you have to figure out how to choose the alphas. And that finally, it took many years, but somebody did figure out precisely how to compute the ordering. So whenever you see a set of parameters that people say you should use, you should think, well, how do I order those parameters? What are those best parameters? And we did some experiments. So for instance, just solving Laplace's equation over a rectangle, and we used 128 parameters. And if you just order the alphas from left to right, after 120 iterations, you got an error of 10 to the 35th. So it grew by quite a bit. But if you use what's called the optimal ordering, it depends upon the gray-black ordering, the error went down to 10 to the minus 7. So if you use this algorithm, it could be very useful, but you have to use it with care. So what are the other downfall is, and this is connected with this too, that if you have these, let's say you have a 7th order polynomial, and you stop it after 3 iterations, the result says it's only good after you get the optimal after 7 iterations. In the computation, you're really computing these partial polynomials, and they're going up and down and so forth. So by just not completing the algorithm, you may get any kinds of result. Now, next time what I'll show is there's another implementation, another way of deriving the Chebyshev algorithm, where you don't compute roots like that I've advocated here, but you compute a sequence of parameters in a very nice way, so that if you go from the kth step of an iteration to the k plus first, it all goes through. There's no difficulty in the calculation. So it's all part of the fun and games of numerical computation, that even though the mathematics may point in one direction, by the time you do the actual calculation, you may want to do something else. Okay, so hope you have a good weekend, and we'll meet on Monday and Wednesday, and not Friday. I'm taking off on Wednesday afternoon, if I'm still alive. And, well, I hope you're getting something out of all this. Thank you. Pardon? Zurich in Switzerland, and Geneva. Yeah. Good.